I'm Daniel Sitanaika, and I'm going to be the moderator for today's session. I'd like to thank all of the sponsors for our tinyML Talks series. So we have DeepLight, Kixo, Edge Impulse, Reality AI, and Maxim Integrated and SynSense. And I'm actually the founding tinyML engineer at Edge Impulse, so I'm super happy to be presenting here today. We'd also like to thank our strategic partner, ARM, who's supporting the whole tinyML Talks initiative. So thank you very much, ARM. Our next talks, which are going to be on Tuesday, November 10th, are from Ehsan Sabori, who's co-founder and CTO of DeepLight, and Alexander Samuelson, who's CTO and co-founder of Imagimob. So that's going to be really awesome. Please tune in, same time, Tuesday, November 10th. We are also hosting our tinyML Asia online summit on November 16th to 19th. So we have currently a call for video posters out. So if you have a poster you'd like to present, abstract to do October 31st. And you can check out the full program at tinyml.org at this URL. So please check that out if you are in Asia. We now have a talk from Manuele Rusci, which is titled GAP8, a parallel ultra-low power and flexible RISC-V based IoT application processor for the tinyML ecosystem. And Manuele is from Greenwaves Technologies. So Dr. Manuele Rusci works as embedded machine learning engineer at Greenwaves Technologies. He obtained a PhD in 2018 from the University of Bologna, where he also works as a research assistant. His main research interests include low power embedded systems and AI powered smart sensors. So I will let you take it from here.
Yeah, thanks Daniel for the introduction. And I would like also to thank the previous speaker to give us an introduction about the topics, which is actually also our main focus topic here. So in this talk, I will introduce to you GAP8, our application processor for the IoT and tinyML ecosystem. And I will try to mainly focus on the set of tools that we have developed in order to bring intelligent function to our devices. I want to start just from a little bit of history to tell that actually GAP8 started in the academia back in 2013 from the PULP project. PULP, which stands for Parallel Ultra Low Power, is a joint project between University of Bologna and ETH Zurich, aiming to develop and distribute open source hardware. During the latest year, within the project, the guys have developed plenty of IPs and hardware blocks ranging from cores, RISC-V cores, peripherals, interconnect, but also full systems ranging from the IoT to the HPC. So leveraging on this experience, actually Greenwaves Technologies has been founded into 2014 based in Grenoble, and they started developing the GAP8 system based on the experience from the PULP project. So afterwards, the PULP project were actually launched in 2018. So what's inside the chip actually? So GAP8 is a fully software programmable architecture, which includes two main parts. On one side, we have a typical MCU architecture featuring a single core RISC-V core, which we name Fabric Controller, plus plenty of peripherals ranging from I2S, I2C, CPI, and many of them. In addition, we have a large L2 memory, which is 512 kilobytes in size, which is connected through the peripherals by means of a micro DMA. So this guy here, the micro DMA, is in charge of transferring data among the peripherals and to the main memory, L2, in the total background with respect to the CPU activities. So while the CPU can run pre-processing on data, just for instance, the microDMA can transfer the net batch of data. In addition to this typical MCU architecture, our GAP8 also includes a cluster, processing cluster, which feature 8 general purpose RISC-V cores that you see in the picture, plus share L1 memory, which is not a data cache, but is a tightly coupled memory. So basically, the data transfer among the L2 memory and the L1 memory should be managed by the DMA guy here, in the total background with respect to the parallel activities of our course. So thanks to this architecture and the full software programmability, our chip GAP8 leads to a high energy efficiency. So we can think about an application which starts from a neutral power state where only the always-on subsystem is on. So basically, we have GPIO or a logic which is sensitive to some interrupt or events in order to wake up the rest of the MCU part here. So once a GPIO is triggered or an event from the RTC wake up the rest, the single core and the peripheral can work to transfer data and apply some pre-processing on the data that we have with a power budget which range up to tens of milliwatts. Then, when we need to elaborate and apply some high-intensive workload on the data that we acquire, we can turn the cluster on. And the power budget now may increase up to hundreds of milliwatts, and the parallel computation may apply to the data. This is totally flexible because thanks to the software programmability, we may apply from CNN inference up to machine learning algorithms or whatever data processing we have in mind simply by reprogramming the architecture. Now, I want to show you just a few examples about the scalability of our devices. Here, I'm referring to a pretty popular benchmarks, which is MobileNet, deep learning image processing based algorithm. So in this case, this algorithm, MobileNet, may be applied for different tasks ranging from classification, image detection, recognition, and so on. And this can be, scale by moving different parameters. So we can apply it on different input resolution and different width multiplier scale. So I can show you here within this graph that thanks to our hardware software co-design, we can scale the system to work on the different models with performance from few millijoule at 66 FPS with the smaller models up to 55 millijoule at 2 FPS with the bigger MobileNet model. And this is done by using the highest performance operating point of the architecture, which is 165 megahertz on the cluster side and 250 megahertz on the fabric controller side, with a power budget of just slightly more than 100 milliwatts. You can find all these examples online on our Github page together with the benchmark results. Another application that I wanted to show you is the automatic license plate recognition. Again, thanks to our hardware software co-design, we were able to port a real-life application to an MCU-class device. Here you can see in the picture the image processing which localized and read the license plate number from a vehicle. So the model in this case is composed by two stages. On the first one, we have an SSD detector which aims at localizing the license plate in the image, PVJ image in this case. Plus we have a deep learning model aiming at reading the license plate, which is based on LPRnet. So what we did in this case is that we optimized the model, scaling the input resolution, plus applying some quantization, 8-bit symmetric in this case, on the same time, not to degrade that much the accuracy of the model. So by doing this, we demonstrate that it's possible to solve this task in an MCU-class devices running at slightly more than 1 FPS of inference time, while performing more than 600 megamach, which is actually the state of the art in the microcontroller-like devices. And the model still features around 4 megabytes of memory, which means that you need to couple it with a small external memory. still your power budget is around slightly more than 100 milliwatt, which is around more than 10x better than other previous devices which implement the same task. So focusing on the methodology, so how can it possible that we achieve this? So I want to start back from the general problem where we have our machine learning problem. So in this case, we have designed a function F in order to classify the data that we have, an image in this case. So the question here is that how can we deploy it on a small devices? So we started by assembling our devices. So we take an imager and we couple it with our GAP8 system. And what we do at the first initially is that we acquire the image and we transfer to the internal L2 memory. Then we turn on the cluster, which will place the computation. And then we transfer the data to the cluster so that the parallel processing will be applied on the data that we have. If we look at the problem from a software perspective, we will have our very typical application code, which is written in C, so fully flexible in this case, which will include, first of all, the acquisition of the data. So we will have some very simple API in order to acquire the data from our sensor. Then we'll have another block of code in order to turn the cluster on. So you see also from here that the cluster engine is totally enabled on demand. And then we will dispatch on the cluster some task, which in this case is the inference of the model. So by calling this API, TI cluster send task to CL, which stands for cluster, we will basically dispatch the inference, the run network inference to our cluster engine. So the question here is that how can we optimally design the run network function, which will be basically play the inference on the data that we have acquired through our sensor. To design with what we have done in Greenwaves, we have developed the so-called GAPflow. The GAPflow is our tool which brings an high-level representation of the model, which might be a graph, a deep learning model graph, but not only, and translate it into optimized C code for GAP. If you look at the scenario from an high-level perspective, we see that the GAPflow actually bridges the two worlds between the deployment on the chip and the machine learning world, where we have, first of all, who usually deal with machine learning. First of all, we usually start with data collection. We collect some data, and this data will be feeding the training pipeline that most of the time will be performed by using the more common use deep learning frameworks such as TensorFlow or Keras. Then once the model is trained, you may need to convert. Just for instance, you may use TF-Lite to convert it into a more compact size. And then this representation will be fed into the GAPflow in order to produce an optimized code for the final target device. So I want to dig more and to show you what's inside the GAPflow. The GAPflow is actually composed by two main parts, NNN Tool first, and then we have the GAP Autotiler. So the flow is actually fed with a graph representation, which in this case is a TF-Lite representation. First of all, the TF-Lite enters within the GAP NNN Tool, which parses the graph and basically applies some sort of parsing and apply some reshape and fuse operation to the several nodes of the graph that has been parsed. Then finally, it may apply some quantization, but I will come back on it later on. And it will produce an intermediate representation description of the graph, which in our world is called the Autotiler model. The Autotiler model is simply the graph description just with a format which is compatible with the GAP Autotiler. This is needed because then the Autotiler will know which is the graph which has to be translated into C code to bring it into the chip. And basically it will produce some optimized code which will be running on the final target. I want to give you just an intuition of the problem which is solved by the GAP Autotiler with this simple representation. So we have on the right side here a graph, which might be our graph, our deep learning graph that we want to port on GAP. And this is now fully described by using the Autotiler model. And then on the other side, we have our system, which is GAP8, which may be equipped with external memories, but this is not necessary, but this is supported, by the way. And then we have developed some optimized libraries, software libraries, which basically apply the building block of the computation running on the parallel cores of the cluster. So we have plenty of basic kernels which are meant to apply parallel computation on data which are transferred to the cluster. So the main challenge here is that how do we optimize the data transfer of the serial tensor of the graph in order to feed the cluster parallel engine? So this is the main challenge which is addressed by means of the Autotiler. So initially, just focusing on a single layer for simplicity, but this will be extended to the full graph later on, the Autotiler will decide where to allocate any individual tensor. And this is done offline by solving an optimization problem based on the memory constraint. Then, since we need to port this data within the parallel cluster, and this memory of the cluster is not enough to transfer all the data, we need to tile. We need to split basically the tensor in order to bring only part of them within the cluster. So thanks to the DMA operation, we will move every tile inside the cluster, apply the computation of the basic kernel, and then bring back the results to the original memory. So all these operations are basically optimized and decided thanks to the Autotiler engine. So just to recap, given the L1, L2, and L3 memory constraint, the Autotiler is able to, first of all, compute the best tile size of any tensor. And this computation is made offline, aiming at reducing the memory latency overhead. Then the Autotiler will produce an optimized code, which basically interleave the calls to the computation building blocks and the DMA transfer. But also it is able to find the best allocation for any individual tensor, which can be either L3, L2, depending on the size of the problem. And this is done, all the computation is done in order to minimize the energy consumption. Coming back to the quantization, because I said before that, of course, inference is done using considering quantized networks. So in our flow, we consider either to feed the GAPflow with a quantized graph, and then in this case, quantization can be placed either at training time, so using quantization over training, or after the training, so using post-training quantization by TF-Lite, for instance. And in this case, the GAPflow will parse an already quantized graph, but can also, the GAPflow can also be fed with a floating point graph. And in this case, we implemented a quantization tool within the GAPflow. And in particular, quantization is done by using the first step of the GAPflow, so the NNN tool. We saw before that the NNN tool is a tool that parses a TF-Lite model and generates the code. Beside of it, it also includes much more functionalities in order to quantize any model. So internally, there is an engine which can run basically inference on the same model as the TF-Lite graph. And by thanks to our implementation of GAP-like convolutional kernels within the NNN tool as well, we can estimate the quantization range of any individual tensor, which will be decided based on a calibration set that we provide to the tool. So in this case, we will be able to, first of all, assess which is the more nicely quantization level, but also to assess a validation on a fully equivalent model of the GAP software. So despite the tools, the GAPflow tools that has been developed for deep learning model, we have our software stack also include many other layers for to allow a user a full flexibility with our devices. So starting from the bottom, we have you can find our RISC-V compiler, which also include all the extension of the GAP chip. Plus, if this is very useful, we provide a simulator, a SOC simulator of the GAP architecture. So anybody, even without having available the chip, is going to be able to run our application on the simulator, which is available on GitHub. So just download it, clone it, and try out our software. Plus, we have other software layers, so the real-time operating system, we support FreeRTOS, plus the PulpOS and Zephyr, and a layer of which we call the PMCs APIs, which also include the BSP to communicate to many different sensors and peripherals. Plus, we also provide multiple application boards. So in the picture, you can see just, for instance, a GAPuino, which is a development board that you can use to develop your own application on our your own application on our devices. Among them, I want just to highlight the GAP8 in this case, which is our application reference platform for occupancy management. So the GAP8 actually include, besides the GAP chip, include a thermal camera from Red, which is 80 by 80 thermal camera, low power. And we also provide the software which basically detects people moving around the room. So this application can be already used and tested to implement your own occupancy management system. And by your own, you can try it out and see that the network in this case, which is SSD based, running 62 milliseconds at the power budget of 4.4 milliwatts per frame per second. And the model has been trained and reached 99% accuracy on an internally collected data set. So if you go actually navigate on our GitHub page, you will be seeing plenty of solutions already available for and implemented on our system, ranging from the GAP8, which I showed you before, but not only. And you will see different examples of deep learning model, but not only, already running in our devices. So we provide example of body detection, face detection, people spotting, and many others. And the list is growing on a daily basis. So next, we are going to release also recursive models, including LSTM, GRU, and so on. So just to say that most of the machine learning applications that are now only available on mobile devices has been already ported to the MCU world and are available today. But the GAP story has not over at all. So actually it's just begun, because we have recently announced the new iteration of our chip. So the GAP9 chip, which will be enrich our family and particularly will be playing a leading role into the audio earbuds market. Because thanks to the rich audio interfaces that has been developed and embedded into the new architecture, plus some sophisticated audio hardware acceleration that will be featuring this new chip. And moreover, we are also developing new and will be releasing new innovative development tools that will make our system fully programmable and totally flexible for your own application. GAP9 will be in mass production on Q4 2021. So this concludes my talk. Here I put some reference in case, just if you have a question, you can drop an email, or if you want to know more about GAP8 and Greenwaves in general, you can visit our website and of course reach out there. So in case you have any question, I will be happy to answer.
So thank you very much, Manuele. We have a question What specific extensions were used for GAP8 to enable ML inference?
The RISC-V cores that are featured by our devices has been extended with DSP instructions. So you will have 8-bit vectorial MAC instruction, so that will speed up the computation there, plus much other instructions like post increment or bitwise operation that will be also leveraged to speed up the computation.
Okay, thank you. Another question, and please post your questions in the Q&A tool if you have them. This question is, what is AT model output?
The Autotiler model is a description of the graph that will be fed to the Autotiler tool. That is our tool that converts a graph into a C code optimized for GAP. So this is just an intermediate representation language that is used from us to feed our tools, and the translation between the TF-Lite graph, for instance, and the Autotiler model is automatically done by the NNN tool. So basically, in practice, the user has not to deal with it.
Okay, thank you. All right, so another question. You mentioned you have also got some LSTM models running. Can you give some examples?
By now, we have released the basic kernels implementing the recursive layers, such as LSTM. So right in the short time, we are going to release full application which leverage on this, and especially we'll be releasing some audio application which include the recursiveness of LSTM.
Okay, so it looks like that's it for questions. So if you have any further questions, you can always reach out to Manuele at his email address that's on screen right now. But thank you so much again for your talk.
You're welcome.
So another big thanks to all of our sponsors, DeepLight, Kixo, Edge Impulse, which is the company I work for, Reality AI, Maxim Integrated, and SynSense. If you're interested in sponsoring the tinyML Talks series, please reach out to Betty at tinyml.org. So here's some specific notes from our sponsors. So DeepLight, use AI to make other AI faster, smaller, and more power efficient. Edge Impulse, where I work, we have an amazing end-to-end workflow that starts with data ingestion, helps you train a model, figure out signal processing, and deploy that model to any type of embedded target. Maxim Integrated, who we saw speak earlier today, their new Max 78000 implements AI inferences at over 100 times lower energy than other embedded options. So now the edge can see and hear like never before. Kixo provide an AutoML platform for embedded AI that builds tinyML solutions for the edge using sensor data. Reality AI provide a set of tools for developing edge AI tinyML models for the smallest MCUs. And SynSense builds ultra-low power sensing and inference hardware for embedded, mobile, and edge devices. They design systems for real-time, always-on smart sensing for audio, vision, biosignals, and more. And again, a big thanks to our strategic partner, ARM, who is helping support the tinyML Talks series. Again, if you'd like to sponsor, please reach out to Betty at tinyml.org for more info. Our next talks are going to be on Tuesday, November 10th from Ehsan Saburi at DeepLight and Alexander Samuelson from Imagimob. Same time, but Tuesday, November the 10th. If you are interested in presenting yourself, please contact us at talks@tinyml.org. And a final mention of our tinyML Asia session, which is going to be November 16th to 19th of this year. We currently have a call open for video posters. So these are 5-minute presentations and our abstract to due October 31st. The full program is available at tinyml.org/Asia 2020. So thank you so much, everybody, for attending, and we'll look forward to seeing you next time. Thanks again to our speakers, and I hope you all have a great day.